All right, thank you everyone. Thank you for the latest Scale ML meetup. And I think today actually we have maybe our best speaker yet. So I'm very excited to have Bill here.
Don't oversell it.
Just to start off a little bit about Bill. Bill is the head of, what is actually, your title is VP of Engineering, but you're actually kind of head of ML and AI for Cohere.
That's right, yeah.
And a little bit about Cohere, actually. Cohere is really one of the most exciting startups that's working in the LLM space. As a startup, it's working to make large language models applicable to a wide variety of use cases, and especially enterprise use cases, so where Fortune 500 and other corporations are using large language models for making workflows and other aspects of what they do much more capable than what they could have done even just a couple months ago. So we're going to have a dive today into Cohere's use of large language models, the work on making LLMs accessible, and really making them easy to use for all kinds of developers. And we'll talk about challenges and opportunities in scaling these models up to longer fine training runs, and honestly, larger data sets that are larger than what we were using even just a couple of months or years ago. And the safety implications of delivering those fine-tuned LLMs to all these various enterprise clients that Cohere works with. Right now, Bill leads a team of 40-plus scientists and engineers in building LLMs to help computers understand a wide variety of language use cases. And he's also a consulting professor of computer science at Stanford. But previously, he was also a director of proactive intelligence at Apple, is a managing director at BlackRock, and a senior research scientist at Google. So my first question to you, Bill. Thinking back on your career, you've had a very interesting career journey. And that list of names, you've moved from academia to finance to big tech. I'm curious, given your career arc, how, why, and where did you decide to join Cohere?
Yeah, well, first, thank you for having me here. It's exciting to be here. It's great to see an awesome turnout here, and I'm really excited to talk about LLMs. I've been at Cohere for about a year, and there were a few different factors that attracted me to Cohere. The first was the focus and agility that comes with being at a startup. Before I joined Cohere, I had been at big companies for more than 10 years. I spent 5 years at Google as a research scientist. I spent a year at BlackRock doing quantitative finance. I spent 5 years at Apple building and leading a group called Proactive Intelligence. And so, a decade at big companies. You were at Apple with me, so I know you can identify with this. And you were at Google as well. Yep. There's a lot of wonderful things about big companies, but there can also be a lot of frustrations at big companies. And I had been involved in a couple of startups earlier in my career, and I really missed the ability to move fast and the ability to change direction quickly. So that was definitely part of the attraction to Cohere. A lot of startups can offer that, and so one of the factors that was maybe a little bit more specific to Cohere was the core technology. The technology that Cohere is built around is the transformer-based neural network architecture, and our founder and CEO, Aidan Gomez, was part of the team at Google that invented the transformer. He was a co-author of the famous paper, "Attention is All You Need." And it's no exaggeration to say that the transformer is the biggest thing that's happened in AI and machine learning in the last 10 years. My field is NLP, and every aspect of NLP, every corner of NLP is completely different now than it was even 5 years ago. And that's mainly because of the transformer. And now it's transforming, not only NLP, but also computer vision and robotics and protein folding and quantitative finance and you name it. So the opportunity to play a small role in advancing this technology and in serving as a bridge between the frontiers of technology and problems that matter to people every day was irresistible. The last thing, and the thing that really sold me on it, was just the people. Before I joined, I had the opportunity to spend some time with the founders and other members of the team, and I was just super, super impressed. Not only with their intelligence and their accomplishments, which kind of goes without saying, but above all with their warmth and generosity and shared values and humility and empathy. And I was just like, this is the kind of people that I want to be around. This is the kind of people I want to build with.
Yeah, that's great. Always super important when you join a new org. You are maybe underselling the impact of this paper. Attention is all you need. I would say it's maybe one of the most kind of groundbreaking insights of the last couple of years in this field. Can you maybe give that elevator pitch for the paper and the key insights that you gleaned from it?
Yeah, I mean, the paper unlocked this new approach to building large language, well, to building all kinds of models, but I'm going to focus on large language models. And large language models are incredibly exciting for a couple of reasons. The first thing for me is just their amazing ability to capture the nuance of meaning and to capture the impact of context on meaning in a way that previous approaches just couldn't remotely do. And I'll give a concrete example of this. So imagine you have a movie review that says something like, the plot was thin, but the star-studded cast delivered a scintillating performance and the visuals were spectacular. And then there's a question, which is, what did the reviewer think about the story? So this is the task of faceted sentiment analysis. You're not asking about sentiment overall, but you're asking about sentiment toward a particular aspect, of a particular facet of the product. And it's a really hard task because, well, for several reasons. One is that the overall sentiment can easily drown out the sentiment toward the particular facet, because you've got all these positive adjectives like star-studded and scintillating and spectacular, and it's easy for that to drown out the plot was thin. Then a second challenge is the question was about the story, but the reviewer said the plot is thin, so you have to connect story to plot. That part is maybe not that hard. The third challenge, which is the hardest part of all, I think, is that the meaning of thin, or the sentiment expressed by thin, is really dependent on context. A thin plot is not good, but thin isn't always bad. If you're talking about a phone or a laptop or something, thin is good. So this is a genuinely really hard task, and I know this firsthand because many years ago, 15 years ago, when I was a grad student, I did a consulting project which was focused on faceted sentiment analysis, and at that time we used kind of classic NLP techniques. We used bag of words and logistic regression and hand-engineered feature representations that captured things about the syntactic parse of the sentence and stuff like that. It was really hard, and the results were extremely mediocre. And so one of the things that I'm astonished by with large language models is how almost effortlessly LLMs can solve this problem, and with really high accuracy, capture all of that nuance and all of that kind of context dependence. What's even more impressive about LLMs for me is that the very same model, without any task-specific training, can not only do faceted sentiment analysis, but can also summarize news articles and extract movie titles from Reddit posts and generate marketing copy and identify toxic tweets and correct transcription errors in transcribed speech. It's really amazing how one model can solve all these problems, and even solve problems that you didn't even have in mind when you trained the model. Things like, I don't know, decoding internet acronyms, or frivolous examples like translating ordinary speech into pirate speech. Just kind of magically comes out of these models. When I first started learning about NLP almost 20 years ago, the whole field was balkanized into these separate subcommunities. So you had the syntactic parsing people and the named entity recognition people and the sentiment analysis people and the machine translation people. And each of these subfields and subcommunities made different models. They used different data sets. They had different approaches to evaluation, different model architectures, different feature representations. And today, you're seeing this great convergence where all those walls kind of fall down, and one model can solve all of these tasks. And the same convergence is actually happening at an even higher level across modalities with models that can handle natural language, but also images and video and so on. So it's just an incredibly exciting time to be working in AI and machine learning.
Yeah. Yeah, given that you worked in NLP, before this current revolution, by which I mean you've been in the field longer than 2 years or 3 years, and the variety of techniques that you brought to bear back then, backwards and logistic regression, do you feel that a researcher starting now, do you understand exactly which techniques that they would go to start with and how they would get started in this field? And is it totally different from what you did back when you were a graduate student and you were first getting started?
Yeah, it's pretty different. I mean, when I was a grad student, it was important to know a lot about linguistics to do NLP. That's one big difference. And these days, it's much less important to understand, to be able to read a parse tree and know what the different syntactic categories are and stuff like that. So I think that kind of prerequisite has completely melted away. And I think that's, in many ways, to the benefit of the field. It's enabled a kind of cross-pollination between very different disciplines in machine learning. You see lots of people who were trained in vision now like coming in and doing great NLP work, and vice versa, people moving in the opposite direction. Yeah. So I think broadly that's been really healthy for the field to have this kind of convergence of different fields of machine learning.
Yeah, that's great. One interesting thing about your background is you've also worked at some of these big tech companies. Apple's one of them. And one interesting thing about the field of ML is there's a perception that you need a lot of really expensive investment in infrastructure in order to work in this field and to train new models. I'm curious how you think about the role that infra plays in this field, especially working at a startup where maybe you have different thoughts on where you can most efficiently spend your resources and your energy on infrastructure.
Yeah, building these models is indeed very expensive and requires lots of resources. It's both data and compute. The best large language models have tens of billions or hundreds of billions of parameters. They're typically trained on something like 1 trillion tokens of carefully cleaned and curated text. So they are indeed very, very expensive to train. It's coupled with one of the really fun things about working at Cohere, which is that we have an honest-to-God AI supercomputer to work with. And for this, we've partnered closely with Google. About a year ago, we announced a multi-year partnership with Google Cloud to provide compute infrastructure and to help us bring our products to market. And Google has been a fantastic partner for us. One aspect of that is that we are now the single largest user of TPUs outside of Google itself. And on a typical day, we're using something like 1.5 to 2 exaflops of compute. So, I mean, that's just a staggering amount. An exaflop is 1 million multiplications per second. So it just boggles the mind. And for a computer scientist to be able to work with this machine, it's like a kid who builds model rockets getting the chance to launch the Saturn V. I mean, it's just incredibly fun. Mm-hmm. It's also a lot of energy. And one of the things that we really appreciate about working with Google is their commitment to renewable energy. All of the energy that Google uses to power our AI supercomputer is produced from renewable sources, and mostly wind power. And we really appreciate that. It's aligned strongly with our values. Also on infra, in terms of software, we use JAX, we use XLA, we use PGIT. This is another area where we've had great collaboration with Google. We have a close relationship with the JAX team and have gotten lots of great support, great advice from them. My hope is that we've reciprocated by helping them to develop the JAX ecosystem by providing kind of constructive product pressure back into them. And then data is another really important input to this process. So it's becoming ever more clear that both the accuracy and the safety of large language models are driven more than anything else by data, by both the quantity and the quality of data that's used for pre-training. So we train on more than 1 million tokens of data. We collect huge amounts of data from the web and from other sources. We invest a lot in ensuring the quality of that data, and so that means things like very careful HTML parsing, smart deduping of documents, model-driven filtering, and so on. And we measure carefully the impact that data improvements have on model quality and model safety.
Yeah, that's great. I used to work at YouTube at Google, and I'd have to request resources through Borg. I think if I had tried to request an exaflop of resources, I probably would have been fired on the spot. but so that's pretty amazing you're able to do it in your partnership. Can you talk a little bit about the difference between the work that goes into training some of these underlying models, generating a new model from scratch, versus the work that might go into what's called fine-tuning the models, making the models applicable to an enterprise use case or a specific use case? Which of those two areas do you spend time on, and what drives your decision to focus on fine-tuning as opposed to training your own model?
It really depends on the customer, the use case, the application. Our main focus and most of our attention and most of our resources goes into training the base models. That's the really expensive work. So we have two different families of models. We have a family of generative models, which are similar to GPT-3. They take a piece of text as a prompt. They give you back more text. We also have a family of embedding models or representation models that take a piece of text and give you back a vector representation of that text. Then we build on top of those models to provide API endpoints that adapt those capabilities to specific use cases. So things like text classification or summarization and so on. And then for customers who have very specific tasks and who have data sets that are kind of representative of that task, we offer the ability to fine-tune the base model to perform that specific task. Now, whether that's appropriate for a specific customer really depends on what application they have in mind, on whether they have data. A lot of our customers kind of don't really have large amounts of data, or they may have just a few examples of data where it makes much more sense to use a few-shot paradigm, few-shot prompting to get the result that they want. But for customers that do have large labeled data sets, fine-tuning can yield much better performance on whatever their task is. In computational terms, it's comparatively inexpensive, and we're constantly looking for ways to make that ever cheaper. So we're investing a lot in techniques for parameter-efficient fine-tuning, where you can fine-tune a quite small proportion of the parameters in the overall model and still get very good results. A lot of our engineering effort goes into ensuring kind of reliability and speed of fine-tuning, just to make that capability much more usable for our customers.
That's great. And few-shot for you does it mean a couple million examples, a couple thousand, 2 examples?
For fine-tuning, it would typically be upwards of, ideally at least thousands. Some customers come to us with millions of examples, and that's great. By few-shot, I actually meant something different, which is where if a customer only has maybe 5 examples of the task that they want to solve, there's an approach to taking those 5 examples and actually incorporating them into the prompt that you provide to a generative model, and basically saying, do more like this. And another one of the miracles of large language models is that actually works. Without doing any task-specific training, you can provide just a few examples of the task in the prompt and get it to solve more examples like that.
Yeah, that seems like, especially over the last few months, to be this incredibly powerful technique that everyone's just wrapping their heads around.
Yeah, it's like black magic.
Yeah. How do you go about thinking about that? It's something that right now seems almost more like an art than a science to understanding what's capable with prompt construction. How do you think about how you're going to systematically approach this space, or do you even systematically approach how you think about building prompts?
We haven't made a great investment in trying to systematize or automate prompt engineering, but I think it's a really interesting area. There is some academic research that has that flavor. It's not something that we've made a great investment in. I think a lot of our customers do come to us with enough examples that fine-tuning is the best path forward for them.
Yeah.
We have lots of, we have lots of experience of kind of playing with prompt engineering ourselves to try to elicit the best performance. I mentioned earlier the example of trying to convert ordinary speech into pirate speech. And this is something that works astonishingly well, just using few-shot prompt engineering. You can give it 5 examples of rephrasing something in pirate speech and then just ask it to do more. And it just kind of works amazingly well.
Right.
And it's really fun to play with things like that.
Yeah. My favorite example I saw around the office recently was a pretty complicated classification task. I think it was like insider trading or a class like that.
Yeah.
And you take the prompt and it does a pretty good job to start. And you change the prompt just slightly by saying, I am a smart computer at the beginning of the prompt. And suddenly there's like a marginal increase in the performance, but enough that's significant.
Yeah.
There's just crazy techniques that work like that I think we're just uncovering.
Yeah.
How do you think about, for these enterprise use cases, pirate speech is obviously a case where maybe there's some sensitivity around it, but not so much as some of the other enterprise use cases you think. And you've talked about doing metrics-driven development, measuring your performance and improving over time. What's the right way to think about adapting these large language models to enterprise use cases where there is objectively a criteria that you need to hit, and you need to make sure that you're hitting certain precision or recall or other metrics that are really important to the customer?
Yeah, this kind of brings in the larger question of evaluation. Like basically, how do you measure, how do you know that your model is good? And this is particularly important when we're talking about a specific customer, a specific application. Is it good for this customer? Broadly, we have evaluation is something that we're kind of obsessive about. And I think that's just part of good machine learning methodology is start by defining success, quantifying it, creating a way to measure it, and then relentlessly hill climb against that metric. Broadly, we have 3 different avenues to evaluation, and I think of them all as kind of complementary. The first avenue is essentially academic benchmarks. So we evaluate our models on a wide variety of academic benchmarks, including some benchmarks that are themselves collections of very diverse tasks, like Big Bench Light, for example. And academic benchmarks are great in the sense that you can run them automatically and frequently during development. And so they're an easy way to evaluate a new approach, to tune hyperparameters, to compare to LLMs from other groups. But many of them are a bit artificial. And good performance on a benchmark doesn't necessarily correlate with good performance on a task that a customer cares about. So the second avenue to evaluation is evaluation on customer-specific tasks. And as I mentioned, many of our customers come to us with labeled data sets that kind of capture what they're looking for. We can use those not only for fine-tuning, but also for evaluation. And this is great because then we know that we're measuring what the customer actually cares about, what really matters for their use case. But of course, those data sets are not public. We can't report those results. And then the third avenue to evaluation is human evaluation. So here we partner with folks like Scale on getting human assessments of the quality of our model outputs. So for a generative model, we'll ask humans to assess attributes of the generative output like fluency and coherence and relevance to the prompt and things like that. And this is great because it kind of represents the gold standard of whether the output is really good.
Yeah.
But compared to automatic benchmarks, human evaluations they're comparatively slow and expensive. Yep. So we don't use them kind of routinely during development. Instead, we tend to use them to validate model release candidates when we think we've got something good.
Can you give a good example of that? And it is interesting because a lot of benchmarks that we use against machine learning models are just objective benchmarks that you can represent through, a video game and how you're actually performing as you're playing a video game. And this is maybe an example where you do need human beings in order to do some of the evaluation. Is there a good example of something where you'd use human judgment in order to inform your release candidate?
Yeah, I think one of the areas where it's been important for us is long-form generations. A lot of the academic benchmarks that are kind of aimed at generative models are not good at evaluating the quality of long generations. No. They're based on, they use datasets where the generative output is relatively short. One of the problems that we saw at one point during the development of our models was a tendency to wander off topic during a long generation. We've also seen tendency to become repetitive after long generations. And existing academic benchmarks weren't really helping us to identify those problems or to evaluate strategies for reducing that. And so it's really important, I think, not to rely too heavily on any one benchmark or even any one of these three avenues to evaluation, but to kind of see them all as complementary. Broadly, they correlate with each other, but the places where they diverge can be really instructive.
Yeah, that's very interesting. One area that sometimes gets a lot of attention in the press, but is just an interesting area to explore and to try to understand is areas where the LLM may produce an output that has some sort of societally bad or really negative outcome. Examples that folks have given have been hate speech or misinformation or other ways where the LLM can be induced to produce a result that you really don't want. How do you think about those scenarios at Cohere, and how do you start to address them before LLM is put into an enterprise use case or a mission critical use case where that outcome could potentially be really, really negative for a customer?
Yeah, I'm really glad you asked about this because responsible use of AI is something that really matters to me, and it really matters to Cohere. In fact, I said at the top that one of the things that attracted me to Cohere was alignment of values, and this is one of the things I was thinking about. I think at Cohere, we're keenly aware that this large language model technology is extremely powerful, and as Uncle Ben taught us, with great power comes great responsibility, and so responsible use is a core value for Cohere, for our founders, for everyone we've hired from the beginning, and something we strive to excel at. This past summer, we partnered with some of the leading LLM providers. We partnered with OpenAI and AI21 Labs to define and publish a set of principles for responsible LLM development. So we articulated principles in three broad areas. They were prohibiting misuse, mitigating unintentional harms, and thoughtfully collaborating with stakeholders. And I'm really proud of Cohere and our partners for taking a strong stand on this and for not dismissing concerns about responsible use. Of course, it's one thing to articulate principles. What's more important is following through by implementing specific measures to mitigate harm.
Yeah, that's interesting. And do you evolve along with customers as they're thinking about this space and they find their new stakeholders within an organization that need to be brought to bear to these sort of problems?
Yeah, this is something that varies by customers. I mean, some of our customers don't really care. We still care, but some of our customers are not really focused on this issue. For other customers, it's really important. So you can imagine, for example, if you're working with a retailer that wants to provide customer support through a chatbot, it's not okay for that chatbot to start spewing noxious stuff. So they care passionately because they want that bot to speak in their brand voice, and they want their brand voice to align well with their company values and their intention in creating it. So this is one of the areas that we think most about. How do we ensure that the output of our generative models is not toxic, does not have profane or obscene content, does not have hate speech, does not have bias, and things like that. There are multiple places in the pipeline where we can intervene to try to mitigate those problems. One is right at the beginning in the data that we use for pre-training the model. We can try to filter toxicity out of the pre-training data. So we're voracious consumers of data. We ingest most of the internet and Reddit and all kinds of other stuff. And you can imagine if we did that carelessly, we would be hoovering up all kinds of noxious stuff. What we can do is use both deterministic and model-driven filtering methods to try to reduce the prevalence of that toxic stuff in the pre-training data, and that makes it much less likely that we'll wind up parroting that stuff back in our generative output. A second remedy is we can fine-tune our base models to promote outputs which are better aligned with human values and human intentions. A third thing we can do is prompt filtering. So this basically means trying to identify prompts which seem to be specifically designed to provoke the model into producing toxic outputs to goad the model into some kind of response, and we can simply refuse to play along. And then we can do output filtering. So we can use a toxicity classifier to look for potentially toxic outputs and fall back instead to innocuous outputs, even if they're less probable according to the model. So it's kind of I think you kind of need defense in depth. It's a complex problem. That none of these measures are perfect, but by having defense at multiple points along the way, you can greatly diminish the likelihood that something bad is going to happen.
Yeah, that's great. Yeah, it sounds like a wide range of techniques that you learn in a particular situation, which one is most applicable to finding this content. That's great. I'll ask one last question before we open up to the floor for questions from the audience. And this is maybe the long view question, although this space is evolving so quickly, and we're talking about capabilities and problems we wouldn't have talked about 6 months ago. So it feels awkward to even ask about what's going to happen 5 years from now. But thinking about the next 5 years and thinking about how large language models are evolving, what do you think the field's going to look like, and what gets you most excited about working in this field?
Yeah, I'll mention a few things. Maybe I'll talk about a couple of things that I think are a little bit closer in, and then maybe some more open-ended long-term things. So there's a couple of opportunities that I think are pretty exciting over the next couple of years. One is neural search. I mentioned that one of the amazing things about LLMs is their ability to capture nuance of meaning and meaning in context. And one place where this can really help is search, because search is about understanding the meaning of documents and understanding the meaning of search queries and connecting the two together. And in fact, within Google, search was one of the places where the transformer and transformer-based LLMs first had big impact. I don't envision us going head-to-head with Google in web search, but I do think that enterprise search represents a big opportunity. Big companies have millions of documents internally that often capture a huge proportion of the institutional knowledge of the company and that they want to make available to their people. And today, enterprise search, by and large, sucks. It tends to use very simplistic keyword matching techniques that don't capture the nuance of meaning at all. So we think this is a big opportunity over the next couple of years. Another one is conversation, dialogue, chat. Personally, I don't get excited about social chatbots, which I think are mainly entertainment. But I do get excited about dialogue agents that help you find information and help you get things done. We've been very inspired by Google's Lambda, which learns to incorporate search into dialogue in a very flexible and powerful way. So Lambda understands when moving the conversation forward requires retrieving some information from the web. It understands how to formulate a search query that will help, and it understands how to incorporate the information retrieved into the conversation in a really fluid way. So that's a great first step. I think we can go much further. And I think the big opportunity is to build dialogue agents that can, in the course of the conversation, learn to invoke arbitrary APIs, not only to retrieve information, but also to take action. So one example of this might be like a flight booking scenario where you need to retrieve information about available flights, but then you also need to take action to book the flight or to choose a seat or to record your frequent flyer number or something like that. Or you can imagine managing your calendar or choosing a health insurance policy or building a 3D model of a new car or something like that. I think language-enabled, this kind of language-enabled complex interaction or tool use represents a really big opportunity for the coming years. I'll mention one more thing, which is maybe this is a little bit more wacky, but one thing that gets me really excited about large language models is what you might call AI-augmented creativity. I think there's a scene in one of the Iron Man movies where Tony Stark is talking to his virtual assistant.
Jarvis.
Jarvis, thank you. Yeah. And he's like, all right, let's game this out. And they start talking about scenarios for, I don't know, something or other. And that's what I'm talking about. I'm talking about like having an AI help you come up with ideas, brainstorm ideas. A large language model can actually help you come up with ideas for product names or for recipes or even for movie scripts. And here's a whimsical example. A guy on my team created a demo that was a date idea generator. So like you give it a location and a season, and it gives you back a suggestion for a date activity. So he put in Toronto and summer, and it suggested roll down the street together in a giant bubble, which, I mean, I think that's an awesome date activity. And he did it again, and it said, get a collection of really bad jokes, take turns telling them to each other, and laugh like crazy people. And like, I mean, it's a frivolous example, but those date ideas are way better than anything I would have come up with.
Those are some killer date ideas.
Yeah, and I just think it points to a really exciting potential.
Yeah. That's interesting. You can also imagine, you know, I love the idea of like AI as like an augmentation of ourselves, but it's almost like bringing out the best version of ourselves in a way that's very hard for us to do sometimes. It's great to think of that.
Yeah.
Well, great. I think we'll open it up to the audience if folks have questions. I think we have a whole bunch of questions, so the tough part's figuring out who goes first.
Yeah. My name is POTUS, like Joe Biden's ad name. My company is called the Pegasus AI. In a nutshell, we have a product that delivers highlight reels faster than any human is capable of editing to athletes. So more like computer vision things.
Yeah.
But my question was primarily, what would you say if you have to estimate the ratio of expense for training these large language models, peddling these massive amounts of data you're suggesting, to how expensive it is to host these cloud APIs per call?
Yeah, so basically I think the question is about the relative expense of training versus serving the models. They're both really expensive. I mean, I talked a little bit about the expense of training. Serving is also really expensive and not to be underestimated. Part of that is just that these models are enormous. Like I said, the best models are tens of billions or hundreds of billions of parameters, huge memory footprint. The biggest models won't even fit on an 80 gigabyte A100. Yeah. That means that serving, you have to figure out ways to distribute inference over multiple GPUs in an efficient way. That's not easy. Inference winds up being really expensive. So we work really hard to optimize to bring those costs down. I don't have a number for you on like what the relative ratio is. I can say that we spend a lot more on training than on inference, but we spend a lot on inference as well. I don't have a precise number for what the ratio is.
Yeah, you mentioned your partnership with Google on JAX, which is another really important framework for trying to speed things up.
That's right.
Yeah.
Hi, great discussion by the way, loving it. So hi, I'm Alan, I'm from Trailheads, an AI consulting company that helps more traditional companies navigate their AI journey from the first steps to putting models in production, so this is all very relevant. So we are at scale, so I have to ask about scale. We thought a couple of years ago that scaling the models and the number of parameters was like the most important thing that you could do. It was kind of the way that OpenAI was showing everybody. But recently, with the Chinchilla paper, we kind of learned that scaling data is much more important than scaling the model size. So there has been like a kind of paradigm shift, and some people are kind of fearing, are we going to run out of training data to train these large models in the near future? And how's it going to look like when probably most of the data generated on the internet is going to be either generated by these models or highly affected by these models, let's say. So what do you think is going to happen?
Yeah, the Chinchilla paper is a paper that looked at whether data and the size of these data sets was a bottleneck or whether the number of parameters was a bottleneck. It had a provocative question posed of whether we're going to run out of data on the entire internet in order to effectively train these models. But
yeah, I think this is a great question. I've thoughts about some parts of that. The last part of it is a real conundrum. But let me talk about scaling a little bit. Over the last year, maybe 2 years since GPT-3 was released, there's been a few different avenues of research in the research community that have all kind of had this common theme of we got results just as good as GPT-3 or even better with a far smaller model by doing X, Y, or Z different. And so Chinchilla was one. It's like just train for much longer, basically. Like you didn't find the right, you didn't find the compute optimal trade-off between training and data, or between parameter size and data. That was a really important insight and one that we've incorporated. Another one I think with a similar flavor was InstructGPT, which is, look, we can get as good, even better performance with a kind of a different training paradigm, using different training data and different kind of supervision. Another great insight. I think of Retro as representing this. So Retro is a paper from DeepMind, which is basically about moving a lot of the burden of knowledge capture outside of the language model itself and making it an external resource that the model can learn to consult as you go. And I think of it at a very high level as having a similar kind of flavor of we can do more with less. These are all amazing insights for the research community. My take on scaling is you can incorporate all of these insights, and it remains true, though, that adding more scale is still going to help. As far as we can tell, we have not yet, even after incorporating all of these insights, we have not yet seen the trade-off between scale and performance flatten out. It looks like there are still gains to be had by building larger and larger models. The question, I think, becomes, is that actually the best thing for the applications that you're trying to build? A lot of the scaling law papers that you see and the graphs that you see, the x-axis is on a log scale. And so, I'm going to oversimplify a little bit, but basically, yep, you can eke out more gains if you increase the model size, the number of parameters, by another factor of 2 or 5 or 10. You can get another point in accuracy on some metric. But does that actually matter that much for whatever application it is? And does it matter? We're very commercially focused, so we're thinking about our customers. Does that matter for our customers? Does the customer really care whether we get 81 or 82 on HelloSwag? Not really, probably. What they often do care very much about is latency. Depending on the application, it matters much more for some applications than others, but many of them care very much about latency, and they would be very happy to sacrifice 1 point of accuracy to get a 10x speed up in latency. So those are the kind of questions that I think become really important when thinking about scaling. And depending on the specific application, the specific use case, building the biggest possible and best, in a sense of accuracy, possible model that you can may not be the right thing. The last thing you mentioned, I don't have an answer for, and I think it's really fascinating. What do we do when all the data on the internet is generated by machines, and we get into this like Ouroboros, where we're pre-training on data that was produced by another large language model? I don't know.
Like inbreeding.
Yeah. Yeah.
Thanks a lot for the talk. I'm Aaron. I'm an engineer at a health tech startup. My question is around how you think about access to these models evolving. Specifically, like OpenAI at first started with the idea that these models should be democratized, but then they also discovered that as you scale up these models, these are very expensive models to be training, and so you have to kind of tap into the capitalism market. So I was curious, especially as we talk about scale, how do you think about access to these models evolving in the future? Thanks.
I think this is a great question, and I'm going to talk about it from two different perspectives. One is what's efficient, and one is what's safe. So let me talk first about the efficiency. These models are incredibly expensive to train, and it's the computational cost, which is, it's often millions of dollars to train one of these. It's the data that you need to collect and curate. It's also, model development depends on highly specialized expertise, which is locked up inside a small number of brains. It's not practical for most of the organizations that could benefit from large language models, and most of the people who could benefit from large language models, to train their own. So in a way, kind of the big idea for Cohere is to centralize those costs and share the benefit widely. That's, in a way, our kind of the central thesis of Cohere, is that those costs should be centralized, and then the benefits should be shared widely. And we see an analogy here to electric power generation. It's not practical or efficient for every factory and every supermarket and every dry cleaner to generate their own power because of the very high capital costs. So as a society, what we do is we centralize the capital cost of power production, and then we distribute the benefits widely through the grid. And modern AI with these giant models, we think, is a lot like that. We see it as our role to amortize that very high cost of development over a huge number of beneficiaries of the amazing power that it unlocks. So that's kind of the efficiency aspect of it. The other angle that you might have in mind is the safety aspect of it. GPT-2 initially was not released because of concerns about danger and about the potential for harm, for misuse. It eventually was, and then GPT-3 was released as well. Well, it's available. It's not open source. It's available for use, but it's not open source. But we do have lots of other models now that are available in open source. You can download all the model parameters, and if you've got the hardware, you can fire them up and do what you want with them. This is a really tricky question, and I don't think I have an authoritative answer to what's the right thing for society. On the one hand, as I mentioned, responsible use is a core value for Cohere, and so we think it's important that we maintain a role in trying to understand how our models are being used and make sure that they're being used for good and not for harm in society. And it's hard to do that if models are open sourced and you completely lose control over how they're used. On the other hand, there is an argument that, like, essentially the horse is out of the barn. And it's it's too late. Let the chips fall where they may. Hopefully, it all works out. Maybe I'm uncomfortable with that. I feel like that's a cavalier attitude towards responsible use of AI, and I get worried about all the things that could go wrong. But maybe it'll work out all right. And there is a point that there are many technologies that can be used for good and for ill. The telephone can be used to do horrible things, and yet we all have telephones. So maybe there's something to that argument. I've never been able to convince myself to be really reassured by it.
Great, thank you, Bill. It's refreshing to hear a really nuanced, thoughtful, considered take on obviously a question that's going to be really pressing to all of us over the next couple of years.
Yeah.
So, yeah, appreciate that. With that, thank you so much, Bill. Thanks for joining us. It's been great to hear about your work out here. And
My pleasure. This was a lot of fun.
we will be following the developments very closely.
Great.